Hello everyone, let's study about the simple pendulum and find its time period and frequency. To understand this, let's recall as to what is a simple pendulum. As shown in the diagram here, a simple pendulum consists of a string of certain length to which a bob is attached. A bob basically means some kind of object as shown here like a spherical ball with some hook onto it. Now here we'll talk about length of the pendulum. So small l is called as length of the pendulum, which means it is the distance between the point of suspension, which is shown here, to the center of mass of this bob. So this L would mean it is length of the string plus the height of the hook, that is height of the hook plus radius of the bob. So it will be the bob radius. This is called as length of the pendulum. That's what small l is. Now here what happens is, if we redraw it by some diagram as shown here, then if we imagine that this part is the center of this system, which means if we leave the pendulum, that is if the simple pendulum is pulled to some end as given here like to end B, and if it is let to oscillate, this pendulum would move from point to B. It would cross the mean position, we'll call as point C, or say some point D, and it goes to the extreme end C. So here B and C are the extreme ends and D is the mean position. So in case of vacuum or free space, assuming that the friction at the point of contact is 0 and also there is nothing present, there is no atmosphere present, in that case this pendulum will oscillate forever. So what happens here is, it would oscillate between the points B and C crossing the point D, where D is taken as here its mean position. You should find out as to what is causing it to oscillate. That's very important. To understand this, let's read out again. So we take a bob of certain length along with a string attached to it. Let's call this a string, and this is the bob. Suppose if you pull it to some angle and leave it here, it would oscillate. We'll first find out as to what is making it to oscillate. The angle which this string makes with the vertical is taken as theta. Then at this point it will have two forces. One force which is mg, which always acts downwards vertically like this, and also there will be a force which acts in the string called as tension. Here these two forces act in different directions. Now to understand a better way, let's resolve the force mg into two components. So we'll take one component which is normal to the tension and one component which is along the line of tension. Now here this angle also would be theta. So this component here would be mg into cos theta, and this is mg into sin theta. So we resolved this mg into two components. To redraw this is what we get. There is tension in this direction and there is mg cos theta along this direction, and there is mg sin theta which is normal to this like this. So we have three forces, but tension and mg cos theta act in the same line but different directions. Therefore tension would nullify mg cos theta, or other way around, T is equal to mg into cos theta. Now what is left out is mg sin theta is left out. So this is an unbalanced force. Now this unbalanced force would pull the pendulum towards its mean position. If we call this as point B and the point C as the mean position, then this force mg sin theta would pull it towards its mean position. But because of this force, the bob would gain some speed. We learned in case of simple harmonic motion that in case of simple harmonic motion, if we have two extreme points and then a mean point. Let's call this as point O, let's call this as C, and this is B. So here B and C are extreme points. When the body is coming from point B towards point O, the restoring force would be towards the point O only. Since in this case the force and the velocity are in same direction, then because of which velocity will keep on increasing. When the particle comes to point O, V would be maximum. So it will be V maximum. It won't stop there because velocity is maximum. Once the particle crosses point O and goes along this direction, the force would reverse because the force is always towards the mean position. So force would be in this direction. Since velocity and force are in different directions, velocity will decrease. So at every point here, velocity will keep on decreasing. At the point C, velocity becomes 0. Same happens here also, except that here it will be part of a circular motion. It will be like this. It will oscillate between these two ends. So we'll call as point, say, D in this case. So it would oscillate between point B and then point D. Again, here also same thing happens. If you look at it, even this extreme end also same thing happens. So tension will be in this direction. It will have two components. So tension would balance. That is, if I draw mg, this tension would balance mg cos theta, and then mg sin theta would act towards the mean position. So it is this unbalanced force which is causing it to accelerate, because of which the particle would cross the mean position and go to the other extreme end. Now here, if we leave at point B or anywhere, this would oscillate. So we need to find its time period. Let L be length of this string. Now let's start deriving it. Now here the unbalanced force is mg into sin theta. Now if you look at this, as point D, it's like a curve here. So we can assume that this pendulum is moving in a part of a circular motion, because you can assume that this BC or BD is part of an arc of a bigger circle of radius L. So it will have a torque. So torque in this case is given as, torque is defined as the product of force into its perpendicular distance. Here it will be, the force here is mg into sin theta, and then here the distance would be its radius, which is L in this case. Now what we do here is, if we assume that if theta is small, then for small angles of theta, sin theta is same as theta only. Therefore what we get would be m is equal to, or tau is equal to mgl into theta. This is what we get. Let us call it as 1. Assumption here is, we have assumed that theta is very, very small. Now we know that tau is equal to I into alpha, where I is its moment of inertia. I is equal to, it is moment of inertia of the bob, and alpha is angular acceleration. So in this case, this I is given as m into distance square. So here this tau is equal to I into I, which is m into distance. Here is a distance from the center to the edge of it, which would be L in this case. So it becomes ml square into, I will put the value of tau from here. Then what we get here is mg into L into theta is equal to ml square into alpha. From here L gets cancelled and also m gets cancelled. So what remains from here is that alpha is equal to g by L into theta. This is what is alpha. It's called as 2. But for a circular motion, so simple harmonic motion equation for a for part of circular oscillation. Here it's not a complete motion, rather it is part of a circular oscillation. So what I get in that case is get alpha is equal to minus omega square into theta, equal as 3. The equation is A is equal to minus omega square into x. This is for linear oscillation, and this is for circular oscillation. For example, as in this case, or as in case of a case of a torsional pendulum, where we have a point of suspension, and then if we have a disc attached to this point of suspension, a disc like this, and if we twist it by an angle and leave it, it will oscillate around the edge of a circle. So in that case, alpha is equal to minus omega square into theta, where theta is angular displacement. Now comparing 2 and 3, we get that omega square is equal to G by L. Now keep in mind here that this minus sign just indicates it's a restoring torque in this case, which means they're same mathematically, because even here also the reason that the pendulum oscillates is because of its restoring torque only. That's the reason it oscillates here. So from this we can say that omega square is equal to G by L, but time period is given as 2 pi by omega is equal to 2 pi. Omega becomes under root of G by L. Therefore, time period is equal to 2 pi under root of L by G. A very, very important expression. Observe carefully here. So even though we had a mass of certain bob of certain mass, but here the time period doesn't depend on its mass. Depends only length of the pendulum. So if we make L to be greater, then time period would increase. Also keep in mind that it depends on G also. The value of G is not same everywhere on the earth's surface. The value of G would vary. So time period depends on G also. A very important point here is that it is independent of the mass taken, which means whether we have a bob here, or we put some cotton, or put some wooden block, doesn't matter at all. As long as the length of the string is same, whether you put a bob like given here, or cotton, or wood, or any material, as long as L is same, T also remains same. This is called as time period for simple pendulum. So in terms of frequency is equal to 1 by time period, that is equal to 1 by 2 pi under root of G by L. So this is the expression for frequency of a simple pendulum. In simple pendulum, there is one subtype of it which is called as Seguin's pendulum. As the name tells us, a Seguin's pendulum is one which beats Seguin's, which means its time period is 2 seconds. That's what is called as a Seguin's pendulum. So if you have pendulum, if you start from some extreme end, we have a bob somewhere here. If you start from some extreme end and leave it, for example from here we leave it, it goes till this point. We call this as point B, this is point C, this is point D. So time taken to go from one extreme end, for example from point to B. So it starts from point to B, crosses point C, goes to point D, and again comes back to point B. So time taken for this would be 2 seconds, or time taken to go from one extreme end to other extreme end. So from B to D, or from D to B would be 1 second. That's called as a Seguin's pendulum. So to find its length, to find for what length would this have a time period of 2 seconds, then use expression t is equal to 2 pi under root of L by G. Now what we want is length of this pendulum. We put t as 2 seconds, that is equal to 2 into pi L by G. If you cancel 2 from here and square it, then what we get is, we get 1 is equal to pi square into L by G. From here L is equal to G by pi square. G is around 9.8 and this will be around 3.14 whole square. To solve it, it will be around 99.4 centimeter, which is almost equal to 1 meter. So this is the length required for a seconds pendulum.